So this is objective 2.1c, and our topic today are piecewise and greatest integer functions. Actually, we're not going to be doing the greatest integer functions today. We're just going to do piecewise. So today's your objective today. You can graph a piecewise function successfully, and you can identify specific intervals that I want to talk about and specific behaviors that I want to talk about. This is not an exhaustive list of the ways that we can describe these piecewise functions. I just want to talk about two specifics today. So if you can walk out of here today feeling like you can do this on your own, we've done a good job. So let's talk about first the definition of a piecewise function. And I'll go slowly so you can get this all copied down. And I'll zoom in a little bit so you can see a little better. So we'll start with the definition of a piecewise function. And let me do a little rearranging because some of my words are off my screen. So a piecewise function, maybe I'm going to be able to do that. There we go. Okay, so a piecewise function is a single function that's composed of functions, plural. So I'm going to put an S on that. Functions defined by specific domain assignments. So you assign certain parts of the domain to the different parts of the function or the different pieces. And something that's really important that people tend to forget is because it's a function, it must pass the vertical line test. And you know, I just like to use VLT. I don't like to write all those little words. The vertical line test. So, I don't like to write words when I can use acronyms. You know what I mean? All right. So, what do I mean by that? So, let's take a look at the stuff over in red that kind of matches my definition. Things that are okay to do when you're graphing a piecewise function. If you have 2 points that are stacked, as long as one of those points is open, it still passes the vertical line test. So it's okay to have 2 points stacked on top of each other as long as one's open, or it's also okay for 2 points to be stacked on top of each other and for both of them to be open, because that doesn't break the rule for a function. Functions cannot have 2 vertical lines. Not okay to have 2 vertical points or 2 vertical line or 2 lines stacked vertically. It's not okay. That is not a function. So, you know, no to that. Okay? All right. So let's just, and it's really common when you first learn to graph piecewise functions to not remember the definition of a function. It says that you can't have 2 points vertically stacked one on top of the other. All right. Now, something that I want to talk about is when we're graphing piecewise functions, a lot of times you're asked to define where the function is decreasing, increasing, and constant. So you'll be asked, what is the interval of increase? Or what is the interval of decrease? Or what is the interval of constant? Okay, so a decreasing interval, you can visually see it on the graph. The graph will be decreasing, falling left to right. You read it left to right to determine that. If the y's are dropping, then it's decreasing. The graph will be increasing, is as you go left to right, the graph is rising. And a graph is constant if there's no rise and no fall. But it's pretty confusing for many people the first round when you're asked to describe these. Often you want to describe the range and not the domain. But you read whether a line or a curve is decreasing or increasing as you read it left to right, not bottom to top, but left to right. So this is going to come on our domain. We have to remember these intervals are domain intervals. And also, crucial that you understand when we are defining intervals of increasing, decreasing, or constant, that we do not use brackets on our intervals, because a point like this is not increasing, it's not decreasing, and it's not constant. It's just a point. It has the what's the word I want to use? The potential to be any of those things. So we don't use brackets ever when we're discussing intervals of increase, decrease, and constant. Never. Okay? So I want to talk about that. Then the last thing I want to talk about is one of the behaviors, and I'm just going to rewrite this. So I'll erase some things here. So behaviors can be one of two ways. I just want you to describe the behavior of the function in one of two ways. The function is either continuous, much like the graph that we saw in the video. All of the pieces ended up connecting to all of the other pieces, and there wasn't a hole or a break or a jump. So if a piecewise function is continuous, all pieces will connect. All of them. And therefore, you can consider the piecewise function to be a continuous function. Okay? You also can describe a graph as being a piecewise function of being discontinuous, which is really important to distinguish in calculus, whether something is discontinuous or continuous, really crucial in calculus. So informally, I'm going to tell you some things that we can describe as discontinuous. A graph can have a jump discontinuity. If it has a jump discontinuity, there will be a gap vertically in the graph. So like, for example, you might have something going like that, and then something going like that. And there's a gap in the graph. Do you see it? But it's a vertical gap in the graph. So you're either jumping down or you have to jump up to get from one piece to the next. So we call this, it's vertical. Okay? If it's a vertical gap, we'll call it a jump. Okay? Another type of discontinuity is called a break. Okay? Breaks, I'll do this in a different color, happen horizontally. So a break in a graph could look at a piecewise function could look something like this. So you'll have a gap in the domain. Okay, so that is what we call a break. And there's one more that we're going to talk about. And again, these are just informal descriptions of discontinuity. The last one is just a hole. Typically, if a piecewise function has a hole in it, it'll be continuous except for in one spot. Something like, for example, I'll grab another color here. Let's say I go like this, and then I open a hole, and then my graph does like that. So you look at it, you go, okay, well, that's continuous, except for it's got a hole in it. So it's a discontinuity at that one point that's been removed. Sometimes you'll call it a removable continuity, but for now we're just going to call it a hole in the function. So we will be taking these piecewise functions that I've put on our note page, and we will be graphing them, describing their intervals of increase, decrease, and constant, and then we'll be also describing them as continuous or discontinuous. Okay, so here we go. Let's start with A. So the instructions say to graph the given piecewise function, indicate the intervals where the graph is increasing, decreasing, and constant, and state whether the function is continuous or discontinuous. So you have 3 tasks to do. I'm going to color code. So this first graph right here is f of x is equal to 4. For the assignment of all x's less than 2. All x's less than 2. So is this a line? It says y equals 4. Is that a line? Horizontal line, right? Where y equals 4. Now, if you're feeling a little uncomfortable with that, you can, of course, make yourself a little t-chart. That's always a helpful tool. Y is equal to 4 all the time because that's what the equation says. Y is equal to 4. And what x's can we use? We have to stay within our assignment here. So I'm going to approach 2, but I'm going to leave it opened because I can't. 2 is not, x equals 2 is not assigned to the first piece of the function, but can't I put 1.9999 there for x? And so I want to approach 2, 4. So I'm going to go ahead and put an open circle there. And then I could also pick 1 for my x. So 1, 4 is right there. So I know for x is less than -2, which goes to negative infinity, that's going to be what that piece of the function looks like. And I'm going to go ahead and label it as a constant just as I go because I'm going, you don't have to label it on your homework as a constant. I'm just labeling it so you can see that that graph, as I look at it left to right, does not rise, it does not fall, it's constantly the same. I'm going to switch colors now to my second function here, which is y equals -3, or actually it says f of x equals -3, but they mean the same thing. And it's defined for all x's greater than or equal to 2. So with this one, if I make a little t-chart, I'm going to include not a -2. I don't know why I did that. Let's just say it's a 2. And I can choose a 3. Will I include 2 as a point in my domain for the second function? Yes. So I'm going to go ahead and put a CL there to remind me to close it. And y in this case is equal to -3 all the time. So I'm going to go ahead and go graph those. So 2, -3, and I'm going to close it. And that doesn't make the function not a function, right? I'm allowed to have that, even though they're stacked vertically because one's open, one's closed. All right. And then that graph goes like that. This is also constant. God bless you. All right. So now that we've graphed our piecewise function, step 1, let's indicate where the graph is increasing, decreasing, or constant. Remember, it's domain related. So it's constant along the interval -infinity to 2. Now you might want to say, but Mrs. Frame, why isn't it -infinity to infinity? And here's why. It's cruising along left to right at a constant rate. And then it gets to 2, and what happens? It drops. And then it's constant again. So you have to use a union to indicate as you're describing it that even though it's constant in both parts of the domain, that it's not constant left to right forever. It's constant for a while, and then it drops, and it's constant again. So anytime there's a break, you have to use a union. Okay? So what kind of discontinuity? This graph is definitely not connected. So it's discontinuous. How? It's a jump discontinuity. So it'd probably be better to write jump discontinuity than discontinuity jump. So I think I would like to revise my answer here. As I describe it, it's a jump discontinuity. Do you have questions about that? I hope that was clear because they get a little harder. All right, so I'm going back to my blue pen, and I'm going to start with this 3-piece function. And I'm going to start with my first one, which is assigning x is less than -1. So I'm doing f of x is equal to -2x. I'm going to ask you a really simple question. What's that going to graph? What shape on my graph am I going to get from y equals -2x? Isn't it linear? Y equals mx plus b. What's my slope? All right, that's helpful because then I can just graph a point and then I can drop my slope in and I can be done and I don't have to do a fancy t-chart. So x is less than -1. So let's put -1 in the equation. -2 times -1 is 2, so y equals 2. So at -1, 2, I'm going to open it up because I'm not allowed to include -1, but man, I can get as close to it as possible on my x. And then let's use my slope. Well, my slope is down 2, right 1, but can I go right? So I have to reverse it and go up 2 and left 1. And up 2 and left 1. Is that a negative slope? For sure. Look, it's decreasing. So if you're not feeling good about that and you just want to go to the t-chart, of course, you can just plug in a -1 and a -2 and you get out 2 and 4. Just remember on the -1 to leave it open because it is not part of that graph or that piece of the function. Okay, I'm going to go to red. I'm going to scoot my graph over a little more so I have more room to work. All right, so here we go. So here we have f of x equals 3 over the interval. The absolute value of x is less than or equal to 1. Now we have to think back to when we learned about absolute value and equalities. So what kind of numbers can go in here? Positives and the answers are always? So can I put a -1 inside here and this be true? Yeah, absolutely. So you have to remember when you drop an absolute value with an inequality, you either have to say you can drop it and you can drop it and set it equal to the opposite and reverse the inequality. So I prefer not to write it like that. So I'm going to write it the other way. But x has to be basically, as long as my x is between -1 and 1, I have a true statement here. So my preference for writing that statement, removing the absolute value, would be to say -1 is less than or equal to x is less than or equal to 1. As long as my x is between those two values, I'm in a good space and I have a true statement. So let's go to -1. If x is -1, what's my y supposed to be? Look, y is equal to 3 all the time. So when x is -1, y is 3. And it's closed because it's equal to. Again, you can make a t-chart. -1, 0, 1, 3, 3, 3. And closed on both ends because it says equal to. So there you have a constant section. And then I got to switch to one more color. We're going to do our parabola. So that says f of x is equal to x squared, defined where x is greater than 1. So up to 1, but not including 1. So let's plug a 1 in, but leave it open. What's 1 squared? Open it up. And that's okay, because we don't want them to be stacked and closed. Plug in a 2. 2 squared is 4, right? Plug in a 3. 3 squared is 9. That takes us off the graph. Remember that this is a parabola and not a line, so it needs to have a curve as it cruises up. And there you have your function. Double check that you didn't mess it up and you don't have double points stacked. No, it's closed because 2 is greater than 1, and so you can graph the 2. All right, so now let's talk about our intervals of decrease. Where's my graph decreasing? Right here, right? So if I'll do it in black here. So decreasing on what interval? We read it left to right. From -infinity to -1, it's decreasing. And then it becomes constant. And it's constant between which points? -1 and 1. Parentheses, no brackets. And then after that, what's it do? It's increasing from 1 to infinity. That's right. So you're describing those behaviors. Now, is it continuous or discontinuous? Discontinuous. What kind of discontinuity is this one? Jump. What's this one? Jump. So again, with the jump, discontinuity. So I'm just here modeling what I'd like to see on your homework. Any questions about that? Yes.
So you said double brackets on the
No. No, because a point isn't constant. A point isn't increasing. A point isn't decreasing. A point is just a location. So when you're, just know that when you're describing intervals of increase, decrease, and constant, you always use parentheses on your intervals. Question? Yeah, you're doing your homework already? Yes. All three discontinuities can happen at the same time. That's correct. List all the types. Okay, here we go. C. I'm going back to my blue pen to do my first piece. So I'm graphing f of x equals x plus 2. That's linear, right? For sure, that's linear. And it's got a slope of 1. So that's always useful when I'm graphing a line, positive slope. So definitely increasing. Defined for the interval x is less than -2. So let's plug a -2 into our equation. -2 plus 2 is 0. So at -2, 0, should I open or close? Open at -2, 0. And if you have to make your t-chart to figure it out, just open it up, -2, plug in, get a 0. Negative slope of 1. So that means you rise 1 and run 1, but I can't go to the right. So what should I do? Left and down. Is that a positive slope? Yep. So that's increasing as I read it left to right. Okay, so first part down, switching to colors. We're going to do this one. So f of x equals x squared. That's the parent function, the quadratic of the parabola. And we're graphing that between -2 and +2, inclusive on the -2, approaching the +2. So let's plug in a -2. -2 squared is 4. Close it. -1 squared, 1. 0 squared, 1 squared, 2 squared, but keep it open because it's open on the x equals 2. So look at what this one's doing. Right now, what's it doing? Decreasing. And then on this side, it increases. And right here at the bottom, it's not constant. That point is not constant. It's just a turning point. Okay, so that one's done. So that's a decrease. That's an increase. Okay, that's good to know. Last one. The third graph here. You have f of x is equal to -half x. I feel like I got a slope going on here. Linear again, right? What's my slope? Okay, so I'm going to drop. So it's definitely going to be a decreasing interval because it's got a negative slope. The graph's going to fall. So let's plug in a 2. -half times 2. -1. Fill it in. You're going to include it. And that's okay because my vertical point above it is open, so that's good. And then it's got a slope of -half, so down 1, right 2. You can pretty much graph the ones that are linear fairly easy just by plugging in your first point in your defined domain. Okay, and that's decreasing. All right, so let's define our intervals. Our graph is increasing from -infinity to -2, and then it stops increasing for a little bit. And then, so we're going to have to create a union because there's a break in where the graph increases. And then it's increasing again from 0 to 2. So those are the two domains where your graph is rising. Then we switch to decreasing because the graph also decreases. On the domain left to right, it's decreasing from -2 to 0, right here, this domain. And then it's decreasing again right here. So we've got a break. from 2 to infinity. And then we'll describe discontinuity. What kind of discontinuity is this? Guys, that's a jump and a jump. So there it is again. On your homework, I promise I put breaks and I did put holes. So you should be able to use those as well. That's a D, discontinuity, jump discontinuity. Okay, on the last one, I actually want to change the problem just a little bit. So here's what we're going to do. On our first one, we're going to make x equal to -1, and we're going to define it in exactly 1 point, which means we have to change the next interval to be x is -1 is less than x. So if you could make those changes for me, just so that you can see something a little bit different. And you know what else let's do? Let's do, well, then that's going to put it, no, I'm going to keep it. So this one's going to be a continuous graph. We'll just leave it like that. Okay, so we're going to start with our first function, -1. So f of x equals -1. So that's a constant function, right? For x is equal to -1, and that's the only x we're allowed to use. So basically, people, that's the point, -1, -1. And that's it. So close it, and that's all it gets. It's a tiny little piece. Not constant, not increasing, not decreasing, just a point. Let's go to the next one. X cubed, so f of x equals x cubed. Now you have to remember what a cubic function graphs like, especially the parent function of the cubic. It looks like this. Okay, so you need to remember that when we go to graph it, because it's defined between -1 and +1. So let's plug in a -1 for x. -1 cubed is -1, but it's open, so I'm going to put a little red circle around that. So we've got some continuity happening here, no jump. Let's plug in a 0. 0 cubed is, and 1 cubed is. But I want to include it or approach it. Approach it. So I'm going to open it up. But I'm not going to connect it with a line. I'm going to connect it with what it's supposed to do, which is that. If you do it wrong, I'll mark it wrong. Last part, we're almost done. Y equals x, or f of x equals x. So whatever x is, y is, that's what we know. For the domain, x is greater than or equal to 1. So we're going to go to, if x is 1, then what's y? 1, right? X is 1, y is 1, and is inclusive. So we're going to fill in 1, 1, and then graph 2, 2, and 3, 3, etc., etc. It's got a slope of +1, so there you go. And there's your graph. So let's talk about some increasing, decreasing behavior. What's it doing? All the time. Increasing. So it's only increasing, and it's increasing from -1 to forever. And continuous or discontinuous? It is continuous. And there you go. And so, do you have any questions? That was a